This video is on area under curve and Riemann sum. And in this video, I want to show the difference between these two notations right here. So the difference is right here. So here we have an example with the function f of x equal to x squared. And if we want the area between 0 and 1 here, and so this yellow region right here. And then to get the exact area, if we use a definite integral, then we know it's going to be the integral from 0 to 1. And then here we get x squared dx. And then evaluate this definite integral, and then we get 1/3. And now let's find the area by filling this yellow region right here with the rectangles. So here I have so what I'm going to do is I'm going to fill this up with n rectangles, and all of the rectangles have the same width. So all of the widths are the same. So for example, like in this case, I have 8 rectangles right here, and all of them have the same width. And so the largest width will be 0.125. Meaning all of them, all widths are 0.125, and the sum of the areas of the rectangles is 0.3984. And so here are the 8 rectangles again. And so what I'm going to do now is, instead of 8 rectangles, I'm going to fill it up with 12. And then I'm going to increase the number of rectangles. And once again, all widths, all the rectangles, all widths are the same. And so we can see here that as the number of rectangles increases, the width of each rectangle decreases. And so the largest width, when n is 200, the largest width will be 0.0099. And so for the largest width, denoted by this symbol right here, which is called the norm of a partition. And then we can see that as n gets larger and larger and larger, and then the sum of the areas of the rectangles are moving closer and closer to the exact area. Recall that the exact area was 1/3 when we, at the beginning of the video, when we used the definite integral. And so this is the case where n increases. As n approaches infinity, the sum of the areas of the rectangles is approaching the exact area of 1/3. And now let's look at a case where n increases, or n approaching infinity, but the sum of the areas of the rectangles does not approach 1/3. And here's an example where as n approaches infinity, but the sum of the areas of the rectangles does not approach 1/3. And so here I've filled the yellow region with 5 rectangles, and here are the x of i's right here. And so in this case, the largest subinterval width will be 0.225. And the sum of the areas of the rectangles is about 0.4417. And now I'm going to increase the number of rectangles to 10. And so the largest subinterval width now is 0.1. And here I have 15 rectangles, and the first 14 here, they all have the same width except for the last one, which is the width here is 0.1. and the largest width, which is denoted by this symbol right here, is called the norm of the partition, and is 0.1. And here I have 20 rectangles, and the norm, or the largest subinterval width, is still 0.1. And so in this case, it doesn't matter how large n is going to be. The largest subinterval width is always going to be 0.1. And because this subinterval width right here does not approach 0, and then so the sum of the areas of the rectangles will not approach the exact answer of 1/3. And so once again here we can see that as n approaches infinity, this notation right here, notation with the limit of this summation is n approaching infinity, does not approach the exact answer of 1/3. And so normally this is why for the exact area we use this notation right here. We use the notation here, it says the limit of the summation with the largest width approaching 0. Because if the largest width approaches 0, then that means all widths will approach 0. And then we'll get the exact answer. Now we can use this notation right here, notation with the limit of n approaching infinity, as long as we can make sure that as n approaches infinity, all widths approach 0. Like in the case where we make all widths the same. And so if all rectangle widths are the same, then as n approaches infinity, then the widths of the rectangles will approach 0. And that will help us get to the exact answer. In summary, we can see that as n approaches infinity, does not always lead to the exact area right here. And so that's why we use the notation to get for the exact area here. We use the notation of limit of this summation with the largest subinterval width approaching 0. And then we can use this notation right here with the n approaching infinity. If we can make sure that as n approaches infinity, all widths will approach 0, like in the case where the widths are the same. And that's the end of the video.